This is Software Engineering Radio, the podcast for professional developers on the web at se-radio.net. SE Radio is brought to you by the IEEE Computer Society and by IEEE Software Magazine. Online at computer.org/software.
This is Philip Winston with Software Engineering Radio. I'm here with Ram Sriharsha. Ram is Vice President of Engineering and Research and Development at Pinecone. Previously, he was Vice President of Engineering and Head of Machine Learning at Splunk. And before that, he worked at Databricks and Yahoo. He is on the Project Management Committee for Apache Spark. Ram has a PhD in physics from the University of Maryland. Is there anything else in your background you'd like to highlight?
No, I think that covers all of it. It's great to be here, and thanks for inviting me.
Great. Before we get started, I wanted to list 2 previous episodes we've done on machine learning, and there are others in the episode history. The first one is episode 391, Jeremy Howard on deep learning, and episode 286, Katie Malone, Introduction to Machine Learning. So in this episode, we're going to talk a lot about vectors. In the context of machine learning, what are vectors?
It's a great question. So people are, I think, very familiar with the concept of vectors. You might have heard it in other contexts. I would say this appears a lot in physics and engineering. Often you're familiar with quantities that have a magnitude and maybe a sign. These are what we call scalars. A good example is temperature, right? Temperature is a scalar. Similarly, there are objects or quantities that have both a magnitude and a direction. You can think of velocity, displacement, acceleration. These are all good examples of vectors. One good way to visualize a vector would be if you're in an n-dimensional space, and if you take the origin and some point in that space, the line connecting them has a direction to that point. And that line you can think of as physically representing a vector. These are concepts that are very familiar to you from non-machine learning settings. They mean the same thing in machine learning.
Okay, for physics, I've done simulations maybe, or computer graphics in 2D and 3D. So in 3D, a velocity vector would have 3 components, X, Y, and Z. In machine learning, we're talking about higher dimensional vectors most of the time?
Yes, that is correct. So the only big difference is the vectors could be 1024 dimensions, even bigger.
Okay. Even people who aren't too involved in machine learning have heard of Google's machine learning platform, TensorFlow. What is a tensor, and does it relate to vectors?
That's a great question. So again, tensor is a concept that may be familiar to people who have been in fields like mechanics or fluid dynamics and things like that. I've heard about these sort of things. A good example is stress on a body, right, on an object. If you think about a small ball or a small kind of cube, you can imagine stretching it and compacting it in 3 different directions, right, 3 independent directions. But you can also imagine shearing it, to kind of applying a force at an angle to it. In essence, to actually measure stress on a 3-dimensional object, you can't just have 3 numbers. You need 9 numbers, right? Basically, 3 independent directions times 3. We call this a rank 2 tensor. So basically, it is a stress energy of a body is a rank 2 tensor. And higher dimensional examples exist of this. So basically, a tensor is nothing but a generalization of a vector. Just like a vector is a generalization of a scalar. You can think of a rank 0 tensor as a scalar, a rank 1 tensor as a vector, and an example of a rank 2 tensor is stress energy, and so on.
Okay, great. So since we're emphasizing the software engineering aspect, I'd like to just talk briefly about specific data types. So in regular programming, I'm usually choosing between floats and doubles for my floating point values. And those today, I think, are generally 32-bit or 64-bit. I've heard in machine learning, they sometimes use 16-bit or even 8-bit floating point numbers. Why does machine learning want lower precision values, and how would I choose what precision to use?
We generally tend to use floats a lot in machine learning, but as you mentioned, 8-bit, 16-bits are also quite common. The 2 biggest reasons to use this are for compactness. These 8-bit and 16-bit representations produce just more compact models. The other reason is sometimes they're actually more amenable to taking better advantage of the CPU, right? So they can actually lead to faster inference and so on. The main trade-off here is between compactness and speed versus accuracy. So you're losing a little bit of floating point precision using 8 bits and 16 bits and so on. So then it's a question of, are you accurate enough for the speed and for the compactness and the storage, reduced storage requirements that you gain?
Okay, great. That gives us a little idea about vectors. Now let's talk about vector embedding. What does vector embedding mean in the context of machine learning?
An embedding is nothing but a transformation or a mapping from one vector space to the other. So a good example could be if you just take an image and look at the pixels of the image. The pixels of the image could be, say, 28 by 28 dimensional, right? So it could be a grayscale image of 28 by 28 dimensions. And I'm thinking of something like MNIST. That gives you a 784 dimensional kind of representation of an image. Now, this may not be the best representation of that image, right? This is just capturing the pixelated version of the image. What you might want to do is to pass it through some kind of a machine learning model that learns a lower dimensional representation that may be better suited for judging semantic similarity between images. An embedding is nothing but that. Basically, an embedding is a mapping that takes some raw representation of your unstructured data like images or text and so on, and produces a smaller, more compact representation that is a better fit for your downstream tasks.
Okay, great. I just wanted to flag one acronym or abbreviation. You said MNIST. What is that?
MNIST is a very popular image dataset. So it's a dataset of grayscale images of handwritten digits, and it's very popular as a benchmark dataset.
Okay. And I'm not sure if this follows directly from discussing embedding, but what is feature engineering? And do the values in my vector correspond to features, or is it not that simple?
Yes. Feature engineering is basically, again, any process that takes a raw representation of your data and produces a more compact representation that's better suited for, say, classification, regression, or any of your downstream tasks. And yes, you're right that you can imagine taking the specific weights of your vector or the components of your vector and treating them as features. Today, a lot of feature engineering comes from deep learning models and so on, where there is not a direct tie-in between the coordinate of a vector or like the actual value of a coordinate to any semantically meaningful feature. But yes, you're right.
Yeah, I was going to ask about deep learning next. When I've looked at a table of context for a course on machine learning, I was surprised there's quite a few techniques before they even introduce neural nets, let alone deep learning. But certainly it seems very popular today. How has the rise of deep learning affected the type of vector embeddings you see or how they're created? Like, what has been the impact of deep learning?
Yeah. So feature engineering has existed for a long, long time before deep learning. Mostly people have been doing handcrafted features. They are pretty time consuming to develop and they require a lot of domain expertise. And in areas like NLP, for example, feature engineering used to mean TF-IDF sort of transformations and so on, which basically generates sparse vectors. What deep learning, I think, has done, which is pretty remarkable, is it has made it extremely easy for anyone to take a pre-trained model and generate good enough embeddings. So you can take these models that have been trained for other tasks and use them to generate features that are useful for training for your task. The commercial viability of this and the availability of high quality pre-trained models has completely unlocked and kind of changed this game. So that is actually why you're seeing a lot of feature engineering being done by deep learning models today, because of the availability of the technology and the ability of these models to produce very high quality embeddings that can transfer to your own tasks.
Yeah, I was going to ask about this term pre-trained later on, but let's talk about it a little now. So the idea is a third party or an expert has done neural net training, done deep learning training, and you use the network they created, but then maybe you add on your own sort of special spin on that, and that's made it easier to people get started in.
Yes, that is 100% correct. Often these are big companies like Google, Facebook, OpenAI, and so on, who have created these very large pre-trained models that have been trained on huge corpuses, and they cost a lot of money, quite frankly, to train. But these models are actually, once trained, they're available for everyone. Even though these models have been trained on these large public data sets, they capture semantically interesting representations that can be useful for your own tasks. So your task may not be anything to do with Wikipedia datasets, but these models are so good that you can actually use them as the starting point to fine-tune for your own task. And again, that has kind of been a game changer.
Yeah, that's great. It sounds like sort of an evolution of open source in the terms of these are open models, I guess, that you're able to use.
Yes.
So going back to vector embedding in the details, you mentioned long vectors, I think 1024 elements. what determines the length? Is that something that I determine as if I'm creating the model, or does the training actually tell me how long the vector needs to be?
This is a great question. So it is what is called a hyperparameter. So it is one of the parameters that's an input to your process itself for creating these models, as opposed to it being a learned parameter. This is basically roughly translates to the number of layers that you may want to use in your model. Again, every task is different, so you may want to have different dimensional embeddings for different tasks. But often what happens is people take one of these pre-trained models and they may use them as a starting point, in which case you get the dimensionality of that model or that embedding as a starting point, and which is usually like 784 to 1024 dimensions and so on.
Okay, you mentioned sparse versus dense, I think it was, for vector embedding. What properties in general does a good vector embedding have, and how am I able to judge that if I'm trying to come up with one?
A good vector representation has to be both compact as well as it has to capture the semantic similarity. So basically, the main reason to create these vector embeddings is that nearness in the embedding space tells you something about nearness in your images or in the things that you care about. So they have to have semantically rich content, but they also have to be compact, right? So that you can store them easily, you can analyze them easily, and you can query them effectively.
That makes sense. So we've talked about vectors and vector embedding. Before we go into vector search and vector databases, I wanted to step way back and give some applications that people might be familiar with that are probably using vector search or vector databases under the hood, just something very concrete that we can think about.
Perhaps a classic example would be Netflix's recommendation sort of algorithms, or in general, any sort of retail product recommendation. The general idea being that if you have users and you know their user preference vectors, and if you have, say, movie ratings and you know the movie rating vectors, then essentially semantic similarity can be used, or vector search can be used to tell you for any new user what sort of movies to recommend, essentially by looking at similarity between user and movies. This sort of idea extends to any sort of product retail recommendation. On the other end of the spectrum, you can also do things like detecting near duplicates in images, right? So if you have an image, and if you have a corpus of images, you may want to find out, is this image a near duplicate of something that's already in your corpus? Now, it is easy to find duplicates, exact duplicates, but images can be near duplicates in many ways, right? They can be slightly grayed out. They can have a small rotation in the image and things like that. It's extremely hard for you to physically quantify what makes an image near duplicate. But if you pass this image through a embedding model, then you can look at the nearness between the two embeddings, and that can be used to tell you whether the two images are near duplicates. So these are a couple of examples.
Okay, great. That makes a lot of sense. It sounds like this is the type of thing we see all the time online these days with services and websites. So yeah, let's move into vector search. So we have our vector embedding. We've created vectors, I guess, for millions of items or many, many items. Are we always searching for similarity, or what are we searching for exactly?
There is both similarity as well as anomalies or dissimilarities. For example, you can look at similar items. You can also look at what is not similar to anything that's in your corpus. And that's usually what we call anomaly. You can also use this for classification sort of tasks, which is you not only retrieve things that are similar to each other, but you can also look at what you've labeled the things that have been similar to each other as, and then use the majority label to predict something. This can be used for classification, regression, it can be used for similarity, it can be used for anomaly detection. Interestingly enough, the set of use cases that vector search powers is growing by the day. And whatever you would have traditionally thought of as kind of search can be thought of as a strict subset of what vector search can do.
So you mentioned classification. Is clustering the same thing? I saw that reference on your website, I think.
Yeah. Clustering is like an unsupervised technique. Classification means you have labels, labeled it for you, and you want to, given a new point, detect whether it has a certain label. In clustering, you're just looking at things that are close to each other. It's an unsupervised technique, and it's very common either as a pre-processing technique or just to identify patterns in your data.
Okay, that's interesting. So there are many types of databases: SQL, key value store, graph databases, document databases. How is vector search similar to some of these existing database types, and how is it different?
Yeah. Database in the category of, say, time series databases or spatial databases and so on, where you have all the traditional problems of a database including data management, including freshness, including transactional updates, and all the things that you care about a database providing, you're dealing with a new type of data, right? In the case of time series data, it's a new type of data. Traditional relational databases aren't optimized for dealing with time series data. Similarly, geospatial, traditional databases aren't quite optimized for dealing with geospatial data. What makes vector search even more interesting, I think, from my perspective, it's not just a new type of data or a new representation of data. It is that vector search is fundamentally computationally intensive in a way that not even geospatial or time series or any of the other databases have to deal with. It's just orders of magnitude more computationally intensive, especially because you're dealing with this high dimensionality problem, and the sort of algorithms that have to do indexing have to be computationally intensive. It stretches the boundary of what databases can do. So it's not easy for you to take an existing database and kind of provide this capability on top of it. But other than that, there is a lot of commonality between traditional databases and what we are trying to do here.
Okay, in a typical database, we construct one or more indices to make searching tractable, where an index is an additional data structure that's constructed from the input data, and it's created and maintained by the database internally. Does vector search require an index, and is it a different type of index?
Yes. Vector search requires a specialized index. It's called a k-nearest neighbor search index is the terminology we use. In that sense, it is very similar to the sort of B-tree indexes or other indices that you would have seen in databases. The place where it is different is that this is basically still cutting-edge research, where it is a challenging problem to come up with indexing techniques for nearest neighbor search that are up to date with your data, right? They're as up to date as your data is, while at the same time being extremely efficient to query. So that is really the challenge that we're trying to solve. But other than that, you can morally or logically think of it B-tree indices or any other index for a database.
Okay, and just to guide us here, what range of scales do you see developers creating vector search for? What is typical, or what would be on the high end of scale for either the vectors you're searching over or the number of queries or any dimension?
Yeah, there's a few dimensions here. One is we see people creating millions of vectors. We also see people creating billions of vectors being searched over. So in terms of just volume, there is a pretty big variance in what we see. There is also other challenges here. For example, we see people who have to update their vectors quite often. These are use cases where your vectors may change very often. We also see people who maybe only create 1 million vectors, but they have to query it with like 100 queries per second or 1,000 queries per second and so on. And we also see people who are perfectly fine with 100 milliseconds or 500 milliseconds or even a 1 second latencies during queries, but they just want to be able to store and query 15 billion or 50 billion vectors. So the set of use cases we see is quite varied across multiple dimensions, whether it is freshness of your index, whether it is query throughput, or whether it is ingestion throughput. So, and we have to optimize across these dimensions.
So just thinking about the implementation of that, are you detecting or inferring like what the usage pattern is and then steering that to a different implementation? Or do you try to have an implementation that can kind of roll with whatever is being sent to you?
So at a high level, we kind of tend to separate hybrid indexes from in-memory indexes. So basically, we have two types of indexes. One that is optimized for storing as much as possible, whereas the other one is optimized for low latency queries. But that said, when we build indexing algorithms, we tend to build ones that are, first of all, highly accurate and have provable accuracy guarantees. But at the same time, they're actually optimized for freshness. So because a lot of our customers actually prefer freshness, we want to build things that are quick to update and quick to kind of react to changing data. So yes, at a high level, we kind of tend to have in-memory indices that are more optimized towards query latency, whereas hybrid indexes that are optimized towards storing massive amounts of data. But we are very careful in designing parts of our system so that they can be reused across these two as much as possible.
Yeah, that makes sense. So you mentioned k-nearest neighbor search. Can you explain a little bit more about how that works? And is the k the number of dimensions in the vector, or is it something else?
K-nearest neighbor search is one of the earliest machine learning algorithms. And the algorithm works like this, which is it basically memorizes the training data set. So basically, suppose you give it a training data set, it simply stores it and memorizes it. So at the time when you give it a query, it looks for the k nearest points to that query vector. And it uses the majority label of that query vector to say that is the label of this query point. The k there comes from the number of near vectors that it looks at. So k equals 1 means it'll look at the nearest neighbor, and that's it. K equals 3 means it looks at the 3 nearest neighbors, and so on. So that k doesn't have anything to do with the dimensionality of the vector space itself, but more how many near neighbors we query.
Okay, that makes sense. Yeah, that's good to disambiguate that. When thinking of the distance between two vectors, the most natural distance function is probably Euclidean, which is the straight line distance between 2 points. But in machine learning, there are a number of different distance functions or metrics. Can you explain what some of these are and why or how you would know to use one of these alternate functions?
Yeah, different distance measures are useful for different sort of tasks. A good example is like Manhattan distance. I think the name comes actually from the way the street system or the grid system is laid out in Manhattan. Right? Everything is right angles there. So if you wanted to travel from one point to the other, you're actually following one of the north-south or east-west grids. So the distance between 2 points in a Manhattan grid is no longer the Euclidean distance or the crow-flying distance. It is really the distance that you travel along the north-south edge and the east-west. So in that case, it makes sense to use Manhattan distance, which is basically the sum of the distances along the axis. Similarly, we tend to see cosine distance being used quite often, especially around text similarity metrics, measures. And the main difference there is that cosine distance cares about the angle between two vectors. It doesn't care about whether one vector is really large or really small, whereas Euclidean distance, it would matter whether the vectors are small or large, right? That would dramatically change the distance between the two vectors. Even if you double the length of a vector, as long as the angle doesn't change with the other vector, the cosine distance doesn't change. So depending on the properties of what you care about in terms of similarity, you may tend to choose cosine distance in some places versus Euclidean.
So can you give an example of maybe where one of these distance functions was inappropriate or would be inappropriate versus one which would be sort of a more natural fit?
Yeah, text similarity is a good example. So one of the reasons why people use cosine distance there is, imagine you just had two words. These two words were the only two words in your corpus. And you can think of them as being laid out in 2 dimensions. One of the words being on one of the axes, the other one being on the other axis. When you have a document, you may have a document that has both of these words, and these words may appear 10 times in one document each. The other document may have the same 2 words appear once each. Now, in the case of cosine distance, the cosine distance between the 2 documents would be 1, because the fact that you scaled everything by a factor of 10 or 100 doesn't change the distance between the 2 documents, which means the 2 documents are kind of going to be very closely related to each other. In the case of Euclidean distance, that may not be true, right? Because the distance now is much larger simply because one of the documents had 100 occurrences of each of these words. So that's an example where you don't want to use Euclidean distance because you care about just the fact that the 2 words co-occurred. The fact that they co-occurred twice or thrice doesn't change that.
Okay, so I can see how it sort of bubbles up to the semantics or the meaning of what you're actually implementing. One more distance function I saw, I'm just curious if you know offhand where this would be used, was the Chebyshev.
Yes, we rarely see it, to be honest. I think it's also called the L infinity distance or something. So basically, Chebyshev distance, if you look at a distance in 2 dimensions, Euclidean distance would be looking at the shortest distance between the 2 points. Chebyshev distance looks at the longest distance you have to travel along an axis to get to that point. I think this comes across more in areas where, for example, imagine that you had a crane and you had to take some package from one point to another in 2 dimensions. But your crane could only move in 2 dimensions, right? It can only move north-south or east-west. And it moves at the same speed in both directions. Which means if you want to measure how long it takes to get from one point to the other, you will use the Chebyshev distance, because all it matters is what is the maximum distance in a particular axis you have to travel, because in that same time, you're going to be traveling in the other axis anyway. So it's an example of that. So it's probably in like warehouse logistics and things like that, you would end up using something like this. But honestly, we don't see that too often. That particular metric I haven't encountered too often.
Okay, that's interesting. I can imagine some distant metrics are more popular or more common than other ones. So you mentioned vector search is computationally intensive. Are these distance functions part of that difficulty? Is that a consideration? Are there more expensive or cheaper distance functions, or is that not really where the cost is coming from?
There is a lot of the cost that we have to pay before we even have to worry about distance functions. The biggest challenge with nearest neighbor search is exact nearest neighbor search is just computationally infeasible, right? So exact nearest neighbor search or the simple algorithm would simply be, if I give you a query point, scan the entire database, you know exactly the distance between each of the query points to every other point in your database, and just sort it and figure out what the top k are. That's like the naive algorithm. That simply doesn't scale. It doesn't scale because the corpus is huge. It also doesn't scale because the number of dimensions is very high. The other challenge that happens, even if you say don't want the exact search and you're okay with approximation itself has challenges in high dimensions. So there's something called curse of dimensionality, because of which once you go into higher dimensions, even designing approximate nearest neighbor algorithms becomes very challenging, right? And any sort of exact algorithm kind of isn't any better than the naive algorithm. So these are the bigger challenges we have to solve. But when designing such algorithms, sometimes some of them may not have good approximation guarantees for a generic metric. For example, they may only have really good approximation guarantees for cosine distance, right? These sort of things we have to worry about. But usually the problems are even earlier than that.
Yeah, I was going to bring up approximate nearest neighbors, since it sounds like that's what's actually used with any appreciable scale. What determines just how approximate the results are? Is that a question of how long you spend evaluating the results, or is it a question of the algorithm? If I have a knob between very approximate and less approximate, how would that work?
When people use the word approximate, it's a little bit hand-wavy, meaning there are algorithms out there that are called approximate nearest neighbor search algorithms, but the extent of approximation is unknown. A good example is things like HNSW. These are really great algorithms, by the way, but there are no guaranteed bounds on approximation. So it's not like you can tune a knob and the more you can tune that knob, the better the approximation gets. It's not like that. That is not the case for algorithms that we develop at Pinecone. In fact, the algorithms we develop have like a tunable knob. So you can actually, if you wanted, tune a knob to get higher accuracy if you wanted. The other thing we do, and also when machine learning scientists talk about approximate nearest neighbor search, they usually mean something very precise, which is they mean that this algorithm is going to give you a point that is within 1 plus epsilon or a small fudge factor away from a point within the distance you care about. You can make this very precise. And those are the sort of algorithms that we develop. So when machine learning literature talks about approximate nearest neighbor algorithms, they have a very strong guarantee, which is there is a trade-off between how close to correct or exact you are versus how much memory and space and time that algorithm takes. But in practice, a lot of algorithms you see out there don't have this property. Very few of them do.
So the vector search portion of, let's say, our machine learning application is not necessarily, or maybe it's not evaluating a neural network at that point. Is that true, or is it possible to have a distance function that itself is learned or itself is a neural network?
By the time we get vectors, in a sense, the training has already been done. So the model has been trained and people are sending the unstructured data through the models to get an embedding, and we store those embeddings and query them. As part of training, you can also do what's called metric learning, which is to actually learn the distance function itself. People can do that. Now, there is no way they can do that on top of Pinecone today, because for us, we get the embeddings, but it's certainly something that people can do. There is a lot of literature on how to do this.
That's certainly a trend we see in software engineering, is that something that was complex and manual is becoming learned by deep learning or a similar technique. So we've talked about vector search. We've kind of veered into vector databases also, but now I want to focus on vector databases and Pinecones. So can you explain what was the motivation in creating the service? What did you see in the industry that this service was trying to meet?
Big companies like Netflix, Google, and so on have been developing this sort of technology over the last few years. A lot of what we do is bringing what has only been available to a few big companies so far into the mass market and making it a SaaS product that anyone can use. So I would say that's what we focus on today. We now know how to do this. And now it's just a matter of scaling it and making it available to everyone. At the same time, embeddings have become very popular, and it's become very easy for people to get millions and billions of embeddings and kind of work with them, which has unlocked a lot of new use cases for them. The main challenge for many of these customers is cost and scale. So if you don't make things 100x less costly, it simply doesn't unlock certain use cases, right? So big companies can afford to spend millions and millions of dollars on some of these technologies, but most companies cannot. What we are trying to do is to bring the cost down to a point where people can benefit from these emerging use cases that they wouldn't otherwise. And since nothing existed that could do this, we started the company around that.
Can I ask what Pinecone stands for or where the name Pinecone came from?
I think they had to change the name because there was like some clash between the original name that we had picked. And we kind of brainstormed apparently for names, and Pinecone was the name that stood out. But as far as I can tell, there's no cool reason for choosing Pinecone.
Okay, we talked a little bit about maybe the interface between what Pinecone does and what the developer or customer is doing. Can you talk a little bit more about that? What am I sending to you? Is the customer hitting your API, or how is that the end user hitting your API? How does that work?
We provide multiple types of APIs, HTTP, Python, and so on. So all you do is you use our APIs. You can spin up as many indices as you want. You can size them however you want. And you get these APIs through which you can submit vectors, metadata to us. You can do data management. You can also do queries. Again, some of this will evolve over time, but today our focus, we are kind of razor focused on building the world's best vector database, which means our focus is on people who already have embeddings. Once you have those embeddings, you kind of send them to us. You can use Pinecone to query it. Over time, we may also kind of start helping people who don't have embeddings, but who have a lot of unstructured data. But today we expect people to have embeddings.
Yeah, that makes sense. So you kind of alluded to this, but what are some more operational challenges with running vector search at scale? What problems did you have to solve that maybe every developer does not want to deal with?
All the common problems of elastically scaling such a service exist. So for example, since embeddings essentially are coming from unstructured data and unstructured data is growing exponentially for customers, right off the bat, we had to build something that had to elastically scale, right? Because people are just throwing more and more data over time. So those cloud elasticity problems already exist for us. But on top of that, what's really challenging is in building the technology that makes efficient indexing possible. So a lot of the time we spend is on how do you ingest data, like large volumes of data fast, and how do you adapt your indices so that they can kind of get up to date fast. At the same time, how do you take advantage of modern hardware, whether it is SSDs, whether it is specialized CPU instructions available on these cloud machines and so on, to drive down the cost for queries and the cost for storing all this data. So most of our time is spent in optimizing for cost, scale, and freshness. And these are all hard problems just because of the nature of vector search being a computationally intensive problem.
Right. One aspect of scaling that doesn't get talked about much is scaling down. I know you give out API keys for people to try the service. I imagine a lot of developers have uploaded test data and maybe they only do a few test queries. Were there any engineering decisions that were specific to hosting this long tail of smaller databases?
Yes. So we have a multi-tenant kind of service that people use. If you have a very small database, in fact, our free tier, if you have 1 million vectors and so on, you can just spin up a very tiny pod. With a small pod, you can kind of do a lot of queries. One of the things we are doing also is things like offloading data to blob storage. So you can spin down your instances and you won't lose data. We are very mindful of those sort of use cases, which may be smaller, and you may not be querying it all the time. But when you need to query it, you need to quickly bring up an index and kind of do your work.
So you kind of mentioned this, but I'm interested for a typical machine learning application, how often the model gets updated. I think you kind of discussed this, but can you give an example of an application where you might perform millions of searches with the same model? The model is calculated just once, or an application when the model needs to be updated frequently? And how does Pinecone support both of these extremes?
Yeah, there are actually quite a few use cases where you train a model once and you kind of create embeddings, and those embeddings are very stable. Often when you think about documents and searching documents and so on, if these documents don't change quite often, you can treat these embeddings as being generated once. And then you're more often searching than updating the vectors. On the other hand, if you look at use cases like advertising, product recommendations, and things like that, user preferences change quite rapidly, right? So especially in advertising, what a user did 5 minutes back or even a few minutes back impacts their decision now much more than what they did days or weeks past. So because of that, user preferences tend to change quite rapidly. And models that use user preferences to do semantic search or any sort of product recommendation style search need to deal with updated embeddings in a much shorter time scale. And we are talking about time scales of less than a minute. So we see both of these use cases. So kind of more common use case for updating vectors quite rapidly is advertising, retail recommendation, product recommendations, and so on. Less common is in the text search or image search areas.
Yeah, I can see that. I saw a lot of examples on your site with natural language processing and a few with images. How do the requirements differ in these two domains or in other domains that you could classify that you see?
Some differences could be as simple as dimensionality, right? So we tend to see higher dimensional embeddings for images, for example. We do tend to see up to 2048 dimensions. Now, higher dimensions obviously means it's computationally more challenging. In text, we usually see lower dimensions, even up to 128 dimensions and so on. We do see that. Other than that, there aren't a whole, again, the size of the corpuses may be very different. So image search, sometimes we don't see that many images. In text search, you could see, if you think about transcripts of sales calls or transcripts of conversations and so on, they can get extremely big. You do tend to see some diversity in terms of just the number of vectors, the dimensionality of the vectors, and so on.
Okay, let's start wrapping up. Related to what you're just discussing, what are the most challenging parts of a developer interested in setting up a vector search application? What do you consider is still hard today?
I think we are working on a lot of the hard parts. I would say that with Pinecone, I would say I'm very comfortable and happy with saying that we've made it easy for developers to get started. We made it extremely easy for you to spin up a Pinecone instance, ingest your data, analyze it, and query it. And people are able to build successful applications with near zero effort. And we strived for that at the beginning. We wanted to make it as simple as possible, humanly possible. Where we are spending a lot of effort is, like I said, in making this as cost-effective as possible. I feel like there is still a lot we can do here to make this technology far more cost-effective than it is today, and also scale it far more than you can do today. Like, for example, we are focused very heavily, but I'm very happy with what we've done so far in terms of being able to reduce the barrier to entry of this sort of technology to a developer. So developers are able to today ingest data and get productive and be able to build applications extremely quickly. And we continue to double down on that.
Okay, you're operating a specific niche within the larger machine learning universe. Where do you see things evolving in general that's going to impact you or machine learning techniques or just any trends that you see on the horizon that you're watching?
The biggest trend, I think, which we also want to take advantage of is while we are working on a very specific niche, which is a vector database, there is this overall trend that data is becoming more and more unstructured. Unstructured data is exploding compared to what traditionally used to be relational data. So more and more of what people are going to be doing with unstructured data is going to be using machine learning, and it's going to be using technologies like what we're building. How do we take what we built today and close the gap with unstructured data, which is today we need people to have embeddings. Today we need people to have a certain amount of sophistication with machine learning to be able to use Pinecone and so on. But there is vastly more unstructured data than there are embeddings. And how do you get people who have a lot of such data and they have really interesting business use cases, but they don't have teams of data scientists and a lot of expertise in machine learning? How do you help them? This is something that we'll have to solve because the amount of data we are talking about is exploding and the use cases are exploding.
Okay, I think that's a great place to end. Can you tell the listeners where to find out more information about Pinecone and then also about you specifically? And I can put both into the show notes for people to look up.
Our website, pinecone.io, has a lot of information. We also have a lot of example notebooks, and we have a free tier so anyone can sign up and kind of play around with Pinecone and give us feedback. We'd love to hear from you. If anything here resonated with any of you, please feel free to reach out.
I'll say that I did look at the Learn section of your website, and I was pretty impressed with the depth of some of the articles, and I found it very interesting. Thanks for your time today, Ram. This is Philip Winston for Software Engineering Radio.
Thank you.
Thanks for listening to SE Radio, an educational program brought to you by IEEE Software Magazine. For more about the podcast, including other episodes, visit our website at se-radio.net. To provide feedback, you can comment on each episode on the website or reach us on LinkedIn, Facebook, Twitter, or through our Slack channel at seradio.slack.com. You can also email us at team@se-radio.net. This and all other episodes of SE Radio is licensed under Creative Commons License 2.5. Thanks for listening.